today's lesson we're going to talk about activation energy, and activation energy is denoted by E with subscript K, and it is the minimum energy required to initiate a chemical reaction. Also, what's important to note is that activation energy will vary with the reaction. So for instance, if we have a reaction of 1 mole of A2 plus 1 mole of B2 gives us product 2 moles of AB, the activation energy is required in order to reach the transition state. And the transition state is a very high energy species, and it actually exists. We're not able to isolate it, and it exists before bonds of the reactants are broken and before bonds of the product actually forms. So if we have a look at the potential energy reaction pathway, we have the reaction pathway in our x-axis and the potential energy in our y. And the reactant A2 or B2 in this case has a certain energy profile, and the product has a lower energy profile, and this tells us if the product is lower in energy, then we have an exothermic reaction. The difference between the energy profiles in the reactant and product is actually delta H, change in enthalpy of the reaction. Enthalpy is a state function. That means that it doesn't matter how we got to product. What only matters is that the reactant gives us product. Alternately, when we're talking about kinetics, and in order to get to the transition state, this is where we denote our activation energy with the red arrow. And that is the energy that is required from the reactant to get to the transition state. So the highest point of any graph in an activation energy profile is the transition state. And the transition state we denote with the square bracket, and we give a double dagger symbol to note that that is a transition state. However, if you imagine now, if we were to add a catalyst to our reaction, now we have changed our reaction pathway, and kinetic profiles, they are path functions because they do depend on the pathway of how we got to product, as opposed to something that is a state function, that is independent of how we got to product. If we add a catalyst lowers the activation energy, which means it lowers the energy that is required to get to the transition state. And the way we show that is that we actually show that the activation energy is lowered, and I noted that with a little green arrow that shows that the activation energy is definitely a lot lower once we add a catalyst. So again, kinetics are involved in path functions because there is a definite pathway that is required in order to get to products. Okay, so let's have a look at the Arrhenius equation right now. The Arrhenius equation is K equals AE to the power of negative EA divided by RT, where K is the rate constant, EA is the activation energy, T is absolute temperature, which is in Kelvin. Absolute means that the temperature is in Kelvin. R is the universal gas constant, 8.3145 joules per mole Kelvin. And A is called the Arrhenius factor, or the orientation or frequency factor. It depends on the textbook, but really what it actually means is that it is involved in the orientation of the molecules. If we think of collision theory, there are 4 factors that are involved in collision theory that determine reaction rate. One of them is how frequently the reactant molecules collide, which is our rate constant. Secondly is the orientation of colliding molecules, which is our A value, our Arrhenius factor. The energy, which is E to the A, the activation energy, and of course the temperature. So the activation energy may be determined experimentally, and if we take the ln of both sides of the Arrhenius equation, we get the ln of K is, with some rearrangement, is the negative EA over RT plus the ln of A, which again looks like our Y equals mx plus B. So if you were to graph the ln of K versus the inverse temperature, so 1 over T, your slope of your line would end up being negative activation energy divided by R, the gas constant, and your y-intercept would be the ln of A. So that's how you can extract activation energy from a graph, if that's what the question asked to do. So once again, the reason why we do that is because it's easier to extrapolate information out of the equation of a straight line. That is exactly why we take the ln of both sides, so we can get it to be a simple straight line equation, y equals mx plus b.